Lecture 5 covers Section 2.5. At the end of today's lecture, you should be able to determine the quality of saturated water. For us to begin, let us recall our vapor dome. Specifically, if we look at a TV diagram, our vapor dome is constructed by adjoining our saturated liquid curve, which is represented by the blue line, with our saturated vapor curve, which is represented by the red line, and these two curves meet at the critical point. Everything existing on the blue line is a completely liquid state. Everything on the red line is existing as a completely vapor state. Now, if we were given a temperature, say 150 degrees centigrade, and we drew a line from our saturated liquid to our saturated vapor state, we would be existing on a line of both constant temperature and constant pressure. Thus, we need one more defining quality to determine where we existed between our two curves. If we recall, a saturated liquid is 100% liquid and a saturated vapor is 100% vapor, we can reasonably surmise that we can exist in a system where we have X percentage of liquid and Y percentage of vapor. That is, whenever a state exists between our saturated liquid and saturated vapor curves, liquid and vapor states are existing simultaneously, and we need to quantify how much liquid and how much vapor is existing simultaneously. Now, the total volume of our system would be that of our liquid and vapor states. That is, our total volume would be the sum of our liquid plus the sum of our vapors. Or this would be the mass of a liquid times our specific volume of our liquid state plus the mass of the vapor times the specific volume of our vapor state. We can determine our average specific volume by taking the total volume of our system per our total mass. We just express our total volume as the mass of our liquid times our saturated liquid specific volume plus the mass of our vapor times our saturated vapor specific volume. And we could divide this by our total mass, the mass of our liquid plus the mass of our vapor. To make this easier, we'll define quality, denoted by the variable x, as a ratio of the mass of the vapor to our total mass. That is, our mass of the vapor per the mass of our liquid plus the mass of our vapor. Thus, we can express our specific volume as the mass of the liquid times our specific volume of the saturated liquid per the mass of liquid plus the mass of vapor, plus the quantity of the mass of our vapor times our specific volume associated with our saturated vapor per the mass of liquid plus the mass of vapor. Everything on the term to the right except nu sub g would be x. That is denoted as quality. Thus, we can re-express our average specific volume nu as 1 minus x times our saturated liquid specific volume plus x times our saturated vapor specific volume, which is also equal to our saturated liquid specific volume plus x times the quantity nu g minus nu f, or nu sub fg. Now, what's nice about quality is it is able to tell us how much liquid and how much vapor we have when we are existing within the vapor dome. If x is equal to 0, we are existing as a completely liquid state, and thus our specific volume will be equal to our saturated liquid specific volume. If x is equal to unity, we are existing as a completely vapor state, and our specific volume would be equal to our saturated vapor specific volume. Now, if x is between 0 and 1, we have a combination of liquid and vapor existing simultaneously. Now note that this expression is only valid between the range of 0 and unity. Our quality can never be negative, nor can it ever be greater than unity. To visualize this, let's look at our TV diagram once again. Our saturated liquid curve, represented by a blue line, would indicate a quality of 0. Our saturated vapor curve, represented by the red line, would indicate a quality of unity. Anything in between would be bounded between 0 and unity. Say we're looking for a specific volume nu, as represented by the dot, about midway between x is equal to 0 and x is equal to 1. We can find this using the lever rule. X would be equal to nu minus nu sub f per the quantity nu sub g minus nu sub f. Let us put this into application and say we want to determine the specific volume and our quality of the following states. Say we have water at 500 kPa and 20 degrees centigrade. Then say we have water at 500 kPa and a specific volume of 0.20 meters cubed per kg. Then say we have water at 1400 kPa and a temperature of 200 degrees centigrade. And lastly, say we have water at 300 degrees centigrade and a quality of x is equal to 0.8. Let us look at the first situation, where we have water existing at 500 kPa and a temperature of 20 degrees centigrade. We'd recognize almost immediately that this is a compressed or subcooled liquid. Our temperature is less than our saturation temperature corresponding to 500 kPa. Our saturation temperature for 500 kPa is 151.86 degrees centigrade. Or conversely, we can say our pressure is greater than our saturation pressure corresponding to 20 degrees centigrade. Our saturation pressure for 20 degrees centigrade is 2.339 kPa. Therefore, we are existing as a compressed or subcooled liquid. Therefore, we know our quality is undefined. Quality is only definable within the vapor dome. We have to be bounded between our saturated liquid and saturated vapor specific volumes. Therefore, we say X is undefined. And to determine our specific volume, all we have to do is look at table B.1.1 and take our 20 degrees centigrade temperature entry for our saturated liquid. Therefore, nu would be equal to 0.001002 meters cubed per kg. Alternatively, you could go to table B.1.4, look at our 500 kPa pressure entry and a temperature of 20 degrees centigrade, and we find we have the same specific volume. Now, at state 2, say we have water existing at 500 kPa in a specific volume of 0.20 meters cubed per kg. If we consult table B.1.2 on page 780, we see that 0.20 meters cubed per kg is existing between our saturated liquid and saturated vapor specific volumes corresponding to 500 kPa. Our saturated liquid specific volume at 500 kPa is 0.001093 meters cubed per kg, and that of our saturated vapor is 0.37489 meters cubed per kg. Thus, we're existing between nu sub F and nu sub G along our line of constant temperature, constant pressure. Therefore, we can define our quality as nu minus nu sub F per nu sub G minus nu sub F. This would be equal to 0.2 minus 0.001093 per the quantity 0.37489 minus 0.001093 meters cubed per kg. And we'd have a quality of 0.532 or 53.2%. Now say we have water at 1400 kPa and a temperature of 20 degrees centigrade. If we turn to table B.1.2 and look at our 1400 kPa pressure entry, we see our corresponding saturation temperature is 195.07 degrees centigrade. Therefore, our temperature is greater than our saturation for our given pressure, and we are existing as a superheated vapor. Our quality is undefined, and therefore we have to go to our superheated vapor tables to pull our specific volume. If we turn to table B.1.3 on page 786, and we look at our 1400 kPa pressure entry and our 200 degrees centigrade temperature entry, our specific volume is 0.14302 meters cubed per kg. And lastly, if we have water at 300 degrees centigrade and a quality of 0.8, we know we are going to be existing as saturated water. If we turn to table B.1.1 on page 778, we can determine our specific volume by taking our saturated liquid specific volume and our saturated vapor specific volume and plugging it into the formula for our average specific volume based upon quality. At 300 degrees centigrade, our saturated liquid specific volume is 0.001404 meters cubed per kg, and our saturated vapor specific volume is 0.2167 meters cubed per kg. Thus, when we put these into our equation, we calculate our specific volume to be 0.0176 meters cubed per kg.